Good morning, everyone. Welcome to the EasyPower Tuesday refresher series of webinars, videos. My name is Jim Chastain. I'm an applications engineer here at EasyPower. And today we're starting a three-part series on Introduction to Protective Device Coordination. And we do appreciate your attendance today. And hopefully this will be information that's useful to you going forward. The EasyPower lineup of modules includes the database editor, which is used to design the one-line diagrams, short circuit, power protector, and arc flash. The module that we use for coordination is called Power Protector, even though we label it coordination in the focus banner. And we're going to be using that feature to describe the vital tools, which are TCCs, for doing coordination. And as we are wont to do, we'd like to start with a couple of poll questions just to kind of see where the audience stands. No obligation and certainly no liability, but it is helpful to get some feedback as we begin. So the first question is, how frequently do your studies require protective device coordination? And I don't want to overemphasize that this is basically aimed at beginners, but the intent, because we cover this subject a lot in day-to-day discussions, and it's surprising how frequently I talk to people that aren't that familiar with TCCs. So that's what we're going to be spending a lot of time, next 30 minutes doing. Let's give it another 5 seconds. Good, thank you. Here's how people have responded on this. So there's a fairly good mix of expertise, or at least need to do coordination. And then the second question is, what areas of the coordination give you the most problem? And again, this is not exhaustive list, basically just trying to cover. We're going to be covering all these topics within this three-part series, and certainly I encourage you, if you can't attend all three, to at least maybe check out the videos after we post them on site. All right, here's how folks have weighed in on this one. And so it looks like the audience is in a good perspective, at least for what we want to do. And let's kind of start with that. Now, today we're going to be basically talking about the baseline, if you will, of series coordination. And the intent of the overall methodology is to prevent equipment damage and improve the reliability of the overall system by preventing unnecessary shutdown of elements of the system that are not necessarily damaged or involved in a particular fault. And to do this, we're going to use TCC plots, and it is a vital tool for coordination. And frankly, the more you know about what's the information that's on a TCC, the better prepared you'll be to deal with the intricacies of doing the coordination itself. And so again, most of the time today, we're going to be talking about the characterizations of a TCC plot, what information it shows on each of the different types of elements in the system, and then start to get into plotting short circuit currents. I think we can cover most of that in the next 30 minutes. So what we're going to begin with is the transformer curves, which are referred to as Z curves. And to do this, we're going to use the EasyPower tools. Now, as I mentioned, if we go back to, let me kind of rearrange my screen a little bit. If we go back to a one-line diagram, this was drawn in EasyPower in the database edit module. And once we've got the one-line diagram completed, then we're able to go into one of the analytical modules. The analytical module that we use for coordination we call power protector, but it's labeled coordination on the focus banner. And when I'm in coordination, that icon is illuminated. Now, what you'll find as you start to use the tool is you have the ability to create and store the TCCs. TCC stands for time current characteristic curves. And as we store them, we're able to look at each of the individual devices. So let's start with a Z curve for the transformer. And it's called a Z curve basically for this approximate shape. And it shows us, and if I kind of rearrange this so we can look at it, it shows us a lot of information. First of all, the TCC curve itself is a log-log plot. And that means, in this case, we're starting down here at, looks like 60 milliseconds. And it quickly goes to 100 milliseconds, then to a second, then to tens of seconds, and then to, excuse me, this is the current. So this is 60 milliamps, 80 milliamps, 100 milliamps, an amp, 10 amps, and 100 amps. Now, you can also notice we're at the 13.8 volt range. So we're talking primarily about the primary current, or at least the effect of doing a reference to the 13.8 voltage. The vertical plot is the time. So again, we're starting at 100 milliseconds, then a second, 10 seconds, 100 seconds, 1,000 seconds. So the advantage of a log-log plot is to get a wide spectrum of information across several different parameters. Now what I've generated here is the full load current for this particular transformer, both on the 13.8 kV side and on the 480 volt side. And so what this is showing us is when we're in a 13H, in fact, the curve itself is, if I fault this secondary bus, the current is meant to determine through faults of the transformer. And so anything that's going to be useful as far as information is the results of the current that's going to be produced on the secondary of the transformer. And the reason, and what the full load current tells us, is these are the maximum currents that will occur in that particular bus, in that particular range for that voltage. So this is normally the full load current for a full load on the secondary side. And so if I position, if you look down here at the bottom band where the cursor is, it reflects the coordinates under my pointer. So if I come up to this mark of the full load current, I see that indeed it's 107, so I'm off by 1 amp. It's 108 amps at this particular voltage. Now if I want to change the reference, I can right click and format, and change the scale to 480 volts, 0.48 kilovolts. And by doing that, it does change the scale both for my current, so I'm at times 100, and the time element. And so now my full load current, when we're referencing the 480 volt side, if I position my cursor up here, now it should be 3106, and if you see the bottom cursor, it's pretty close. We can zoom in and get it closer. Now, that's the maximum load current. If I double click on this bus and fault it, this is the maximum secondary current that we will see if there's a downstream or a through fault. Likewise, it tells us on the primary side that the maximum current for a downstream fault or for a through fault is 1.23 kiloamps or 1,000 amps. Again, any current above that level, 1,230 amps, is due to an internal fault or a fault on the primary side of the transformer. In either case, it's a bad situation and we need to be concerned about that. Okay, now in terms of the properties of the transformer, what we're looking at, again, the full load current was based upon the calculations on the voltage and the impedance of the transformer. If we open up reposition my plot here a little bit. If I double click on the transformer icon itself or on the plot, either one, the tool will open up the dialog box for that element. So here we're looking at the TCC temporary tab for the TCC window for the transformer itself. These two curves are a result of these check boxes over here. So let's kind of start with the 100% withstand curve. If I apply the check boxes, I get one curve that's basically dotted format. The upper end of the curve, which is the longer time, lower amperage, is due to thermal damage. The bottom part of the curve is due to mechanical damage. So the higher current will cause potential damage to the windings, either because of the inrush shock and torquing the curves, or just overstressing them so that they have mechanical damage. If we plot the derating or unbalanced curve, we get the solid, and this is a 58% derating for use with a delta Y transformer. Turns out in the delta Y transformer, the ground current is important for a single line to ground fault on the delta side. Excuse me, a single line to ground on the Y side. So a delta Y, which is what this transformer is, if I have a single line to ground fault on the secondary, then it's going to sense or be sensed in the primary side by current in all three phases. And it will be 58% of what the normal damage curve would be for a phase, a single phase or a three-phase fault. So anyway, if we have a delta Y with a Y grounded secondary, then for ground faults, we need to make sure we use this line. Now, if we check the frequent fault curve, and all this is described, all these terms are described in ANSI C57.109, which is the standard for oil-filled curves, or IEC 765.4. There's a different standard for the dry curves, but they have the same reference points. Now, if we apply the frequent fault curves, that gives a shift in the Z shape to our curve, and these are described as the potential based upon the definition of terms and the voltage in the standard, the ability to survive some faults that exceed this particular current in certain transformers, as long as you don't exceed the 100% withstand. So that's in reference to frequent faults. Now, the coordinates are plotted based upon these settings here. So the maximum plot time that we have set up is 500 seconds. That can be set to 1,000 seconds. And if we do that, we can see now that the curve extends up to the full current value, the full load current. And we can reduce that if for whatever reason we want to look at a smaller portion of the curve. Now, if I kind of move my curve up a little bit, you'll notice there's a dot down here that's called the inrush, and that's determined as a multiplier of the full load current. So in this case, we have a typical multiplier of 8x. If we change that, and it lasts for 12 cycles, that plot will change position. And the significance of this particular point is that this could be the current and time coordinates at the first energization of the transformer when we turn the equipment on. So any protective device we have to protect the transformer can't be sensitive to this particular current and time, or it'll trip unnecessarily. So any protective device that we have upstream of the transformer has to have its set points or its trip settings above and to the right of this particular data point. What else do we want to talk? So resistance grounding. In addition, if we come in and say, okay, on this particular part, I wonder if we can, not sure we can change it. Let's go back to our database. So the point about the impedance curves of the 58% derating is a function of the grounding curves. So if we go in and change this transformer to a grounded transformer by putting in a resistance, a high resistance value, let's say 10 amps, now we show a ground, a high resistance ground on the transformer neutral or the secondary. Now when we go into our coordination and plot this curve, we only show the single current because the ground current is going to be very, very low at a maximum of in the 10 amp range. So it won't, no matter what we determine as far as the derating, it won't show the unbalanced curve. So for those of you that have a high resistance curve. Okay, so that's stomping all over the transformer. Now, if you'll notice, we've already created these plots in EasyPower and saved them in our list of TCCs. When it comes time to protect that device, normal primary protection involves a fuse. The fuse is this fat red line, and the protection is based upon the current value as it touches or exceeds this upper right hand boundary of the red fuse. The width of the fuse itself is based upon the manufacturer's spec and tolerance level between the lowest sensing value and the upper fusing or clearing time of a particular fault. And so in terms of what we want this fuse to do, we want it to protect as much of the transformer as we can and still allow the full load current to be available on the secondary side. I'm going to close this plot. And the next one we're going to look at is a motor. So let's look at a motor plot. Again, the motor is the load. And so what we're looking at here is the maximum current that this motor will recognize as a good current or a good start. And so we have a chair typical plot that's determined by the description of the motor that we entered when we drew the one-line diagram. So first of all, the horsepower was generated, and then the TCC or the X over R calculation is made, and based upon that we get the plot for that starting curve. The acceleration time determines how long it takes to get to this particular area. When we first close, if we look at the lowest time that's plotted on this curve, we see it's at 40 milliseconds. And we show here at the lowest time element, when we apply voltage across the curve, it instantly takes more than, well, if we're at times 10, so there's 10, 100, 1,000. So it takes something over 1,000 amps to get it off the dime when the motor's dead stop. And then it takes this amount of time, which we have listed as 2 seconds, to accelerate up to speed. If the acceleration time is longer than that, and by default we'll have that filled in for that type of motor, it makes that adjustment on the time it takes to get up to speed. So at that point, once we're up to speed, as long as the time current plot is, again, the left of the curve, it's considered a normal start. And now we're talking currents in the 30 or anything, frankly, less than 100 amps, which is quite a bit different than the 1,000 that we started off with. So again, the shape of this curve is determined by these settings. And most of this time, when you plot a particular motor, these are set up by default. The thermal limit curve is activated by this checkbox. And I want to know where that is when I'm doing series coordination, because that's the point where there's potentially thermal damage to the motor if it maintains a stalled position or a locked rotor for any amount of time. And so that time we have set up between 6 and 20 seconds, and that value can be changed if you have specifics on the motor. And the idea then is to have our protective device activate if that line is exceeded or before that line is exceeded. Likewise, on the tail of the motor during the initial start, there's an asymmetric surge that is affected by the X over R changing over time, and that's a factor of this inrush current right here. If we have a value that's 3 times, which is basically double the inrush that we started off with, we see a more pronounced tail on this curve. So again, our protective device needs to be to the right of the bottom of this curve, in fact, to the right of the chair all the way up, but inside of the thermal damage curve, and sometimes it's a little bit of a tedious task to accomplish that feat. Cables. Let's do a breakers and cables. So cables are a linear curve. The higher the current, the quicker the thermal damage will take place. But again, these are a function of the insulation properties and the current carrying cross-sectional ampacity. And they will be straight lines that you don't ever want to exceed, because that's cause for thermal damage in your system and the wiring. Now, a breaker, we have 2 different types of breakers here. The one downstream is a molded case circuit breaker, and if we look at the specifications, we can see it has a thermomagnetic trip unit. Well, the thermal part is this sloped area, and the magnetic part is this instantaneous tripping at the bottom. And they're determined by the phase trip settings. If we have a different sized breaker, we can see that and the width of this column is set by the manufacturer. And again, what he's saying, as long as we are using this in the proper application, the right-hand top of this plot will indicate where the breaker is guaranteed to clear. Now, in terms of coordination, it's very difficult to coordinate a molded case circuit breaker with an instantaneous setting, as if you have anything upstream that has an instantaneous setting as well. Oh, a couple other things I wanted to show. On the breaker, when we look up at the short circuit tab, this number comes from the device library. So if we found the part number in the device library, the interrupt rating will be on the data sheet for the part itself. We have the ability to clip the TCC curves based upon the setting of this particular tab. If we have none, then there's no clipping, and in some cases it can be a little confusing, or it's unnecessary to look beyond this, because the maximum current we'll see is, in this case, the momentary current, which is 9,879 kiloamps. So the choice to limit the current at that point is ours. In this case, we've set tick marks for momentary, which is a half cycle current, interrupting, which is the 5-cycle current, and then 30-cycle long-term short circuit. Likewise, on a low voltage power circuit breaker, which has a trip unit, in this case, there's a setting for the manufacturer's trip unit, and we're seeing that this is set up for long-term, short-term, instantaneous, and then ground selections. And so we can go into our set points, and based upon these settings, we set up the long-term pickup. And again, we're talking about the magenta breaker. So let me turn off molded case circuit breaker. So a low voltage power circuit breaker with a solid state trip unit, we have the ability to use clipping if we need to, or if we want to, or none. We have the ability to put in tick marks, and by removing the TCC clipping, we also show that the ground settings. And then when we get into coordination, we will talk about the recommendations to set the long-term pickup and delay, the short-term pickup and delay, and then any instantaneous settings. And again, there may be some cases where we don't want instantaneous if there's going to be a problem coordinating with the downstream multi-case circuit breakers. So again, we'll get into more details on the breakers next section. I did want to talk about a motor control protection circuit, which is it's only a magnetic device. There's no thermal protection at all. And so in that case, we would have this as a motor protection primarily. And then this part of the curve, the upper tail, is the ability to utilize a motor overload contactor. And by plotting that, we can make sure that the curve falls inside that thermal damage curve for the motor itself. So it's a pretty useful combination of capabilities where we don't want a long-term pickup setting, but we do want overload protection during the start. Oh, I did want to point out that on the plot, we are showing asymmetric curves, asymmetric currents only. So this value where the plot is clipped is 29,897 amps asymmetric value. We're looking at half cycle current over here, and we see there's a 26,930 amps. What we're looking at, if I look at the TCC options, in my one-line diagram, we're looking at symmetrical and asymmetrical current. And the point I want to make is that during the first half cycle, that difference is fairly significant. So this 29,900 amps equates to this plot of value on this tick mark. Now, if I'm looking at the 5-cycle current, that difference starts to decrease because the contribution current and the X over R value from upstream or other motors decreases. And by the time I get to the 30-cycle current, that asymmetric value in the motor contribution is declined to 0. And so the asymmetric value equals the symmetric value. Over here, what I want to show is on my curve, that's going to be reflected in my trip settings or my tick settings for 30 cycles and interrupting. So at 30 cycles, that current plotted here will equate to the asymmetric and symmetric values at 30 cycles. So sometimes people ask the question, why the difference? And the difference is a matter of time. Time is not part of this plot, and so I make up for it using the tick marks. Time is a reference on this plot, and so that's why I can show asymmetric and symmetric both. Okay, looks like we're about out of time. We will pick up the discussion next week or next session with protective devices, and then jump into some recommendations for coordination. Appreciate everyone for attending. Let's see if we got any questions we can answer. Fuses and breakers in relation to transformers. We'll cover that next week, Harold. It is an issue, and what you'll find, in fact, it'll be worthwhile going back to this plot. What you'll find is that fuses are less of an issue when we have downstream protection. So if I kind of show you my fuse plot, what you'll find is that sometimes because of the downstream load requirements, we may set a fuse up with this perspective because we're going to have a downstream breaker that will protect the transformer even more effectively than the fuse, which is going to have issues at this upper end or of the low current fault. And so we will get into that detail specifically next week. NEC for the IEC. Robert, you're asking a question about the NEC 517. And I guess I'm not sure what you're asking. The point about healthcare, yeah, I'll have to research that. Robert, I'll answer that one next week as well, because I'm not familiar with NEC 517. The bottom line is coordination is difficult with multi-case circuit breakers, and for the most part, we're not that involved with personnel safety when we're talking about coordination, but we'll get specifics on that for next time. Thanks everyone for attending, and by all means, check the website for upcoming webinars, and we'll talk to you all next time. Have a good day.